Hello everyone, we're going to continue with chapter 18 now. Do the next couple sections, one on thermal expansion and one on phase changes. For thermal expansion, so people are familiar with a thermometer. So for a thermometer, you have this pool of mercury and then a whole bunch of things. So mercury goes up to some level, looks something like this, and you read off a level. Now what happens if someone comes in and heats the thermometer? Well, the liquid is going to take up more space. There's what's called volume expansion of the mercury in the tube. And so this thin tube, so the volume of the mercury goes up by a little bit. As long as this tube is thin enough, you can really track those changes in volume, which can look pretty drastic as long as this tube is thin. And so we mark different temperatures on this thermometer based on where that liquid rises up to. So thermal expansion is an important property that materials have, and they're useful in things like creating a thermometer. So I guess to look at this, thermal expansion. So I guess I'll just begin with the general comment that things tend to expand when you heat them. So if you have a rod of length L naught, and you heat it, so going from here to here, we're going to heat the rod, the length will expand. So it gets a little bit longer. And it makes sense that the amount that it increases is going to depend on how long the rod is. So imagine you had two such rods, and you put them side by side. So in addition to L naught and another one, well, both of these are, if you heat them up both the same amount, then they're both going to expand by the same amount. And then put the two final ones together, it's going to expand by twice as much. So the formula that we're going to write down is going to talk about the fractional increase in the length of the rod. Okay, so the formula of how to relate the delta L with delta T is going to involve fractional change in length. So suppose I heat it up so that the change in length is 1%. If that's the case, then this fraction would be 0.01. So this is the fractional change in length due to thermal expansion. Delta L over L is equal to some constant times delta T. And that constant we're going to label with an alpha. So this is the key equation that we're going to start with when it comes to thermal expansion. Okay, so a couple comments. First of all, delta L over L, fractional change in length, is a dimensionless number. So this thing alpha is some quantity that when we multiply by a certain number of Kelvin, or degrees C, more on that in just a second, then we get a unitless quantity. So alpha is going to be some constant it's a number per Kelvin. So here are a couple characteristic quantities. And notice how they're called the coefficients of linear expansion. Coefficient of linear expansion. Okay, so this has units. So here we see that the table is in per degrees C. So for example, alpha for aluminum is equal to 2.3 times 10 to the minus 5. Now you can write this as 1 over degrees C, or this is the same thing as 2.3 times 10 to the minus 5. So notice how it's the same number per Kelvin. And the reason for that is that, remember, a delta T of 1 degree C is equal to a delta T of 1 Kelvin. It's only when we're talking about the overall absolute temperature of, say, 273 Kelvin that's not the same thing as 0 degrees C. So temperature changes of degree C or Kelvin are the same thing. Now, if we wanted to convert this to per degree Fahrenheit, this is where the number will change. Now, if we increase the temperature of 1 degree Fahrenheit, that's not as big a temperature change as 1 Kelvin or 1 degree C. And so this number is going to be smaller by an amount 5/9. Remember, that was the ratio of relating the two temperature scales. So this would be 5/9 times 2.3 times 10 to the minus 5 per degree Fahrenheit. Another way of doing this is to just take our original number and then multiply by how many degrees C is in 1 degree F. And you should be able to get this factor of 5/9 from this. Okay, so another thing I want to mention here is that so basically the alpha that you're given tells you what units your delta T need to be in. So it doesn't matter whether this is 1 over degree C or 1 over degree F, as long as you multiply by the appropriate delta T here to cancel out that unit. Okay, so another thing that I should clarify here is, so this L right here, is L the initial or the final length? Notice that this number, this alpha, coefficient of linear expansion, is very, very small, 2.3 times 10 to the minus 5. So if I multiply by 1 Kelvin, 10 Kelvin, even 100 Kelvin, the fractional change in length is not going to be very much, a fraction of a percent. If that's the case, it doesn't matter. So the answer to this question is L the initial or the final, it doesn't matter. Whether you plug in the initial or the final one, it'll be about the same fractional change in length. So you might say, well, what if delta L over L is very, very big? Well, in order for it to be very, very big, like of order 1, the delta T needs to be so big that you probably don't even have a rod anymore, right? If you're increasing the temperature by 10 to the 5 Kelvin, you've probably already melted the rod or boiled it or whatever. So really, it just in most problems, it doesn't matter. We'll just call it L naught, just because that tends to be easier. That tends to be the thing that you already know from the start of the problem, and the point of the problem is to find L final. So a lot of times we'll just plug in L equals L initial, but really it shouldn't matter if the product of these two things is a number much, much less than 1. Okay. Now, I want to be able to answer this question here about the metal disc with a hole. But before I do that, I want to talk about fractional increases in area and volume, not just length. And to motivate this, I want to look at just a square. And let's suppose that the initial length of the square was A and A. Okay. And suppose we heat, so what about delta A over A? So we already did fractional increase in length. Now we want to look at fractional increase in area. So suppose we heat this up so that this grows by 1% in each direction. So heat so that each side has delta L, delta length over L is equal to 1%. If that's the case, then the new area is going to be 1.01 A squared. Right? Each side is going to increase by 1%, so it becomes 1.01 times A. And so I'm going to rewrite this as 1 plus a small quantity squared, and then factor out the A squared. And this is approximately equal to 1 plus 2 times 0.01 times A squared. If I rewrite this as A new over A old, and I can actually subtract off an A squared. So I can rewrite this A new, as a delta A new minus A old divided by A old. This is going to be 2 times 0.01, or 2 times 1%. This would be 2%. So in other words, if delta L over L is 1%, then delta A over A is 2%, And you can probably guess that delta V, volume over volume, if we had a volume of material, is 3%. Okay, so your book doesn't talk about delta A over A, but it does talk about delta V over V, and it has a quick motivation. And so here I just did an approximation by the binomial theorem. We're using Taylor expansions. Your book talks about it in terms of differentials. So volume is proportional to L cubed. If you take a differential of both sides, you get dV is 3 L squared dL. So you can see where that factor of 3 comes in as well. What we're working towards here is that there's a relationship between the coefficient of linear expansion, the thermal coefficient of linear expansion, and the thermal coefficient of volume expansion. So another key equation that we want to know is that delta V over V is equal to a constant times delta T, again. And this constant, we normally use the letter beta for it, the coefficient of volume expansion. And if you have a material that's a solid, you can write this in terms of alpha. This is 3 times alpha times delta T. So the fractional increase in volume is 3 times the fractional increase in length. So this is utilizing the fact that this quantity, delta V over V, is small. That's why we can get away with just working with the differentials. Okay, so now so this stop to think is basically the same question as what we have. So now we're in a position to answer this question. And it's a little counterintuitive what the answer is. I'll try and give 2 explanations, but it still probably won't make sense even after both the explanations. This is just something you have to think about for quite a while. Okay, a metal disc with a hole inside. If we heat up the disc, does the hole get bigger or smaller? Okay, so let's think about this 2 ways. So we're going to answer the original problem. We're going to have 2 different answers. 2 answers to this problem. So we're going to heat this up. Does the hole get bigger or smaller? So the first answer that I want you to think about is, so what happens if we had a solid disk? Maybe I want to get that out of the way. So we have a solid disk. And we just, someone took a Sharpie and they just highlighted where the hole used to be. Before, so imagine someone didn't cut out a hole from a solid disk, but they actually just had a solid disk and they put a Sharpie right there. And then someone heats this up. Heat up so that the fractional increase in area is whatever, 1% or something. So you could solve for what temperature that needs to be using our equation. So if we heat this up, this whole thing, the whole solid thing, is going to get bigger. Oops. This whole thing is going to get bigger. Every piece will expand. So if this hole was halfway out, it's still halfway out. And notice how the hole is going to get bigger. Okay, so the diameter is going to increase by some fractional. So if it has some initial diameter, and this is the final diameter, then that's a length. And so delta D over D naught is equal to alpha delta T. The area of the whole disk is going to satisfy delta A over A is equal to, now because it's areas, we're going to have 2 times alpha delta T. Now that's true of the big area, that's true of the whole, and that's also true of this area right here. So actually, if you just subtract the 2, you can show that it still satisfies this equation. So this area right here is still going up. So this shaded area, the area of just this region, so just the ring, satisfies this equation right here. Delta A over A is 2 alpha delta T. That's true for the area of the whole thing, that's true for the area of the hole, and it's true of the annulus, of the ring right there. So that is to say that because even the hole gets bigger, so remember this is still solid metal right here, this piece right here also gets bigger. So the hole gets bigger. So you might say, well, why doesn't the metal just, this metal is going to expand, why doesn't it take up the space right there? It expands everywhere outward. So the best way for this thing to expand is for it to expand outward everywhere from that point. So really it doesn't know that it needs to expand outward from that point, but that's just, everything is pushing on its neighbors. And so if you sum up all the effects of pushing on your neighbors up from here, everyone's going to wind up going outwards. Even this inner circumference right here. Okay, so another thing, another way you might want to think about it is, well, okay, so we have this hole right here. So imagine you just had a ring of metal right here. Ring of metal. And we heat it up. What happens to the length of that ring? Well, the length is going to increase according to our equation for thermal expansion. So delta circumference, so I'm going to use the letter C for circumference. Delta circumference over the original circumference is alpha delta T. And this is going to be positive. This is some positive number if we're heating this thing up. So that means the final circumference is bigger than the initial circumference. That means that this radius must have grown. Right? So if we heat this up so that the fractional increase in length is 1%, the fractional increase in circumference is 1%, the radius goes up by 1%, that means that this hole gets bigger as well. Right? So you could think of it as, you can think of the solid disk with a hole as just a bunch of rings, and all of them are going to increase in their circumference, and so they all just expand outwards. Okay. So really that just takes a while getting used to think about. Other problems are more straightforward, just plugging in the number into that formula. So the only thing to keep track of is, is the expansion linear, or are we talking about areas, or are we talking about volumes? And by the way, for liquids, it doesn't make sense to talk about a length or a area. And so that's why this table, it just gives beta for these liquids. There's no corresponding alpha. For something like brass, you could relate alpha and beta. So you could also talk about beta for brass. You would take the alpha and then multiply by 3 to get the value on the table right here. Okay, the next section is on phase changes. So to motivate this section, I want to explain this plot right here. Phase changes. So suppose I start with a piece of ice, and I'm going to keep heating this up. I'm going to keep, so I have an ice cube at T equals 0, and we're going to heat this up at a constant rate. So put a flame next to it and keep the flame next to it. So right now, so far we haven't been quantitative about what this word means, heat right here, and really we're going to save that for next chapter to be a little bit more quantitative. But you can imagine that you can pour energy into it to try and change the temperature. Okay, so we're going to heat up this ice cube, change its temperature. And this plot, I want to keep track of what's the temperature of the H2O as a function of how much heat added. So heat, I'm using the letter Q for this, for heat. So what happens? Well, the ice cube will start off at some temperature that's below the freezing point. And we can heat up the ice cube. So the ice cube heats up, heats up, heats up. There becomes a point, though, at 0 degrees C, or 273 Kelvin, whichever you prefer, where the ice cube can't heat up anymore. It starts to melt into water. And then at a certain point, so at this point it's all ice, at this point it's all water, and then for points in between it's some water, some ice. So this is more ice, this is more water on this side. And then once it's all water and we keep adding heat, the temperature will go up again. And then once we hit either 100 degrees C, or you could write it as 373 Kelvin. Notice I'm writing these equal because I'm saying the temperature is equal. A temperature change of 100 degrees C is equal to a temperature change of 100 Kelvin. So notice how going from here to here, the delta T in Kelvin is the same as the delta T in degrees C. So then we get another phase change. So this right here is just ice. This is just water. The phase changes, though, so let me just finish this off. The phase changes, oh, maybe I can call this is steam. And this is, you're seeing why I wrote H2O, because ice, water, steam are all H2O, but they're different phases. Steam or gas. Steam, which is a gas. So these horizontal parts are called phase changes. So this is a phase change going from the solid phase to the liquid phase. So this is called melting if you're going one direction, or freezing if you're going the other direction. So freezing or melting depending on which direction, and we have a word for either one of these two. If you're either freezing or melting, it's referred to as fusion. And so later on you're going to encounter a formula where you'll hear terms like the latent heat of fusion. That has to do with the energy associated with going either way, whether you're going to the right or to the left. This involves fusion. And this one right here involves either boiling. So this phase change right here is boiling or condensing. And for this one, we use the word vaporization. So you'll hear the word latent heat of vaporization. And normally you think of vaporization as being one way rather than the other. So vaporization is used for either direction. But yeah, so these two are phase changes. It takes energy to change the phase of H2O and any other quantity as well. All right. Now, how would you know whether H2O is ice, water, or steam? Well, here, just from this graph, you could say, well, I could just read off, if you told me the temperature, I would know exactly what phase we're in. But everything, this whole plot was made at 1 atm. So it's assuming, this whole plot is assuming that we're at 1 atm, atmospheric pressure. If you have different pressures, you can have different phases. So sometimes you can be at a pressure where you go straight from ice to steam, and there's no water that can ever exist at that pressure. So to keep track of this, we have what are known as phase diagrams. So notice how the axes here are pressure and temperature. So a phase diagram keeps track of, if I knew the temperature and the pressure. So here, at 1 atm, if I knew the temperature, I know what phase I'm in. Maybe I'm on the boundary, but I know I'm a combination of those two. So really, you need to know the pressure and the temperature. So pressure on the vertical axis always, and temperature on the horizontal axis always for these phase diagrams. We're going to deal with plots in the next few chapters. Most of the time, our plots are going to be pressure and volume. So keep in mind that this plot is different than the ones we're normally going to work with in the future. So this is just special. These axes are special just for phase diagrams. Water looks like this. Now there's two special points that I want to talk about for these phase diagrams. So it's the 2 points in black, that one and that one. So those have special names. For water we can have all three phases of matter. So this is solid right here. This whole region is, the material is a solid. This one right here is liquid. And this whole region is gas. Okay, so if I said a pressure and a temperature and you're right here, I know the thing is going to be gas. I know also that at 1 atm, water can have all three things. It can be a solid, liquid, or gas. So I know atmospheric pressure is going to be somewhere up here. So 1 atm. By the way, we're drawing just the phase diagram for water, but there exists one for all sorts of different, there exists one for every different material. So 1 atm, I start with a solid. If I keep heating it up at constant pressure, I get to a liquid. And if I keep heating it up, I'll get to a gas. So to jump over these lines requires some energy. So we have to, we have to keep heating it up before we can actually get a change in temperature there. We have to go, so crossing over these boundaries are what correspond to the phased changes in this diagram. You'll notice that if I'm at a pressure higher than 1 atm, and it's a lot higher, so this figure's not to scale. So there's a special pressure right here, 218 atmospheres. And notice how in this diagram, it looks like there's no such thing as boiling past that. So if I'm at a really high pressure, there's no drastic transition from a liquid to a gas. It's just some fluid where the density will change gradually. So one characteristic of these phase changes is that something changes very, very drastically. So like, so for liquid versus solid, normally the density will just go down by like a factor of 1,000, just all of a sudden. So you're at almost the same temperature, but the density will change by a huge, huge factor. That doesn't exist if you're beyond this critical point. So over here, we just call it a fluid. So it's either a gas or a liquid. It's a nice smooth transition between the two. We don't have a good way of distinguishing for points outside of this point right here, outside this critical point. So we just call things a fluid past here. And you might hear this referred to as supercritical fluid. Okay, we're past the critical point. So this point right here where this transition, there no longer exists a transition, is called the critical point. So that's where there ceases to be a clear difference between liquid and gas. There's another point that's very, very special, and you'll notice that that's where all three phases can coexist. That point is called the triple point. So it's the triple point because you can have all three phases coexisting. So you could have a vial of ice, steam, and water all in equilibrium. So it could just exist indefinitely. For water, that exists at a lower pressure than 1 atm. Right? So the only other thing is that you might not be so used to is this word sublimate. So if you're at such a pressure, so if you're at a pressure underneath the triple point, you can go directly from solid to gas. And that's referred to as sublimation. That doesn't exist for water at room temperature. You have to go to a really small pressure, some pressure under the triple point pressure of water. But that does exist for CO2. So this is the phase diagram for carbon dioxide. You'll notice that at 1 atm, there doesn't exist. There's no such thing as liquid CO2 at 1 atm. It sublimates. It goes straight from solid to gas. So at room temperature, CO2 is a gas. If you kept cooling it, it would just turn into a solid. It would just totally skip over the liquid phase because you're at a pressure under the triple point. Okay, at higher and higher pressures, the other main difference between these two, between water and carbon dioxide, one main thing is that at higher and higher pressures, notice how water tends to go towards the liquid phase. So liquid is a higher density than ice, which is why at higher and higher pressures it tries to get to the more dense phase. Whereas for most materials are more like carbon dioxide in that the solid phase is more dense than the liquid phase. Yeah, that's about it.